Alright, the objective of this lab was to examine the motion of a spring mass system where the mass swings in an arc while oscillating from a spring. Then we would use Tracker to extract the position of the mass in the video and model an identical system in VPython using Newton's second law and the energy principle. And then we would compare the accuracy of my model to the actual motion. My modeled system follows the actual motion for the beginning of the video in Tracker. Although there is a little of a difference as time goes on, there are some forces and some reasoning to the reason behind why there is a difference. And a couple of these reasons could be the inaccurate tracker plotting and the increased effect of the drag force. For this experiment, I chose the Earth, spring, and mass all together as my system. Alright, and there are two principles going on with this lab. There is Newton's second law and the energy principle. Newton's second law predicts new velocities and resulting new positions. The energy principle tells us that the change in total energy must be equal to 0. And here is my Tracker video. I calibrated Tracker with the given length and placement axis to where the spring is attached. After marking the point mass for the entire system, Tracker graphed the x and y values for me, and I exported these values into a CSV file so Python could read them for compiling the data. We are only really concerned about the y-axis because this is the direction that the spring stretches, which we can then relate to Hooke's law, F equals kx. To find the period t, I subtracted the first time from the last point and divided by how many completions the oscillation went through. So to explain that more thoroughly, so for y, I went to the lowest trough point. So that was like a little over 8.2, and the first point, which is a little less than 0.8, and I subtracted those and divided by 5, and the total time was 7.5 seconds divided by 5, so I got the period as 1.5 seconds. And then given the period found earlier, we can calculate the three initial values. 1. Use the formulas for period to solve for the spring constant. 2. Solve for the length of the stretching spring by letting Hooke's law equal the gravitational force. And 3. Finding the relaxed spring length. Then we can import these values into the code in addition to the mass of the object swinging and the position of the ball. These values can be found from Tracker. There are three forces at play in this lab. There's gravity, spring, and the net force. The gravity and spring forces are interacting with the mass, and the net force is the sum of the forces. Gravity is subtracted from the spring force because it is in the opposite direction of the spring force. So when we calculate velocity using the principle of Newton's second law, we then use the net force here, which includes the force of the spring, and also there are three energies of this system. There is kinetic energy, gravitational potential, and spring potential. And the energy principle that I brought up earlier tells us that the sum of these energies should be equal to 0. The first code block here is the initial energies, and the second code block is the energy changes of the system. To update spring position, two components need to be updated: length and tilt. L and the spring axis spring.axis respectively. Subtracting ball position by the spring position will give us the length. Dividing by its magnitude will give us the position vector, L hat. Subtracting magnitude of length from the original will give us the stretch, S. Finally, To graph the axis, we use the position vector L. Alright, time to take a look at the model. In this model, the red ball is from the tracker video, and the blue ball is of the actual model. As you can see, they follow a very similar path at the beginning of the video and then start to veer off at the end. The lag and difference of path is caused by the slightly inaccurate point mass plotting and the drag force, like I stated a little earlier. The blue arrow is the spring force and the black is the gravitational force. And the black arrow is always pointing down, like we can see on your screen now. And the blue arrow is always pointing in the direction of where the spring is and towards where the spring is attached. I also had Tracker output all the energies of the system on a graph. The blue curve is of the kinetic energy, the red curve is spring potential energy, and green is gravitational potential energy. If all the energies are summed up, they equal 0, the yellow line. For question 1, this follows the law of the energy principle, saying that the sum of energies in the system equals 0. Question 2 asks to compare the x and y periods. I already had the y period, so I used the graph method of finding an average period time for the x period. The x period was 1.61 seconds, and the x and y periods are different because the spring is swinging further in the x direction than the y direction, giving an elliptical shape of motion, with a longer side of the ellipse along the x-axis. The x distance, calculated from the x period, should be greater than the y distance. Using the y period of 1.5 seconds, I got the y distance to be 0.3779 meters. And then using the x period of 1.61 seconds, I got a distance of 0.3997 meters. This satisfies my previous statement that the x distance is larger than my y distance.